mechanics and apply quantum mechanics and use that to understand two model systems, a particle in a box for a continuous spectrum of energy and a continuous spatial distribution of matter. Now, there are three main laws that govern Newtonian mechanics. The first law tells us that when viewed from an inertial reference frame, an object at rest tends to stay at rest, and an object in uniform motion tends to stay in uniform motion unless acted upon by a net external force. Now, what does the second law tell us? The second law tells us what happens when you apply a force. This says that the net force F on an object equals the time rate of change of momentum, leading to the famous equation F equals ma. The third law tells us that every action corresponds to an equal and opposite reaction. Now, to cast these laws into a mathematical formulation, various formulations exist. One that is particularly useful is known as the Lagrangian formulation. This formalism is based on the principle of stationary action. The Lagrangian L of a particle is defined as the difference between its kinetic energy T and the potential energy V. Now, in generalized coordinates, the energy is given by. Now, in this equation, Q stands for the generalized coordinate of space. Now, from this, we can define a quantity called the action S. Now, this is simply defined as the integral of the Lagrangian between two given instants of time, say t1 and t2. Now, what does the principle of stationary or least action tell us? It states that the classical path taken by the system between times t1 and t2 is the one for which the action is stationary. That is, the change to first order is 0. Now, in other words, we're attempting to take the path of least action. Seems like a useful principle to have for life as well. Now, mathematically, for a small change del q, this principle states that the differential change in action impulse to bring out the distinct difference between classical mechanics and quantum mechanics. The first example will be 0. Further, let's assume that at time t equals 0, the particle is moving with a velocity v. That is, x dot is v. Note that in this notation, dot here refers to a time derivative. Now, this results in the equation of motion given as the position x is given as velocity times the time. Now, what does this tell us? The equation of motion tells us that we can precisely locate where the particle will be at any given instant of time. It's a very classical phenomenon. There is no restriction in the value that the velocity v can take. So therefore, the energy of the system can have a continuous spectrum. That is, it can take any value. Now let's move on to a second example. Now let's assume that there is a potential, and the potential well is a harmonic potential field. Now a harmonic potential field is one where the external potential goes as the square of the displacement x. Now what is a good example of a harmonic potential field? Now if you have a spring and try to stretch it, the energy from its rest position is well described by a harmonic potential well. Now, what is the motion of the particle in this case? Once again, we can derive the equation of motion from the Lagrangian equation. Now here, it turns out that the solution of the equation of motion consists of two sinusoids with a phase difference of pi over 2. Now we can invoke the same initial conditions that we used in the previous example, and this leads to the equation of motion where the position x scales as the sinusoid of frequency times the time, where nu is a characteristic frequency associated with the system. In this case, the characteristic frequency scales along with the constant k and the mass of the system m. Like the Lagrangian formulation that we learned, another formulation called the Hamiltonian formulation of classical mechanics describes the equation of motion, albeit using a different quantity, h, called the Hamiltonian. Now the Hamiltonian is defined as the sum of the kinetic and the potential energy. Now for the second example that we studied, the Hamiltonian of the particle, it turns out that it would be independent of time. Now from these two examples, we can infer some key conclusions about classical mechanics. Classical mechanics predicts that the particle motion is completely deterministic, that is, the conditions of a particle at any given instant of time will chart out its future trajectory. The Lagrangian formulation teaches us that the particle traverses along a path such that its action s is an extremum, that is a minimum. Now we discussed two examples. The first example taught us that a free particle, one that does not have any influence of any external potential, will maintain a constant velocity as proposed by Newton's first law of motion. Second example told us that the motion of a particle in a time-independent potential field, classical mechanics, the particle motion is not restricted to a single path as would be predicted by classical mechanics. Instead, all possible paths have a probability of occurring. Now, we can define the probability of going from 2 to 1 in terms of a total amplitude k, such that the probability p is given as the square of the amplitude k. Now, using the previously defined quantity s, that is the action for a particular path, the total amplitude can be considered as sum of contributions from each and every path connecting 1 and 2. Now, the actual contribution of each path can be determined in terms of the action using the following relation. Note that all objects are really quantum mechanical in nature. That is, they traverse along paths with probability. Now, in this case, the Hamiltonian operator consists of both the kinetic energy part and the potential energy part. Let's now define x to be the distance of separation between the two atoms. We can now write down